So we have one more example to sort of finish up this idea of properties of definite integrals. So release multiple choice question. If I know the integral from a to b of f is equal to a plus 2b, then can I simplify this definite integral? So I'm going to try to rewrite that integral so it looks more like this, because I know the exact value of that integral, or some other integral that I can evaluate, either because I understand how to find the area using geometry, or the one other way to find a definite integral that I know is that I know how to find the area under a constant curve. Again, it's by thinking about the shape as geometry. So if I'm going to have the integral from a to b of f of x plus 5 dx, I'm going to rewrite that as the sum of two integrals. That's the integral from a to b of f of x dx plus the integral from a to b of 5 dx. So this part I know is exactly equal to a plus 2b. And I'm going to have to add whatever I think the integral from a to b of 5 is. So two ways to think about it. I guess you only know one of them so far. I want to find the integral under the curve y equals 5 between a and b. Well, since y equals 5 is a horizontal line, this shape is going to be a rectangle whose width is b minus a, and whose height is 5. So if this was not a multiple choice question, you could write this answer, and it's fine. But I have to simplify my answer enough that it looks like one of these. So that's going to be a plus 2b plus 5b minus 5a. I just distributed the 5, which I can simplify to 7b minus 4a. Okay, all the way back in chapter 2, we talked about how to compute average velocity. We said it's distance traveled divided by the time it takes. But now we know that distance traveled is area under the velocity curve. So we have a new way of writing an expression for average velocity. This is going to be distance traveled, which is the area under the velocity curve between two times, call them time A and time B, divided by the difference, the distance across that time interval, right? So that's b minus a. So I can write average velocity as 1 over b minus a times the integral from a to b of the velocity function. It turns out that this kind of idea, the average value of a function, doesn't just apply to velocity functions. We're going to use it on all kinds of different functions to talk about the average value of a function. So you're going to want to know this guy by heart, and there's a place for it on your important facts paper. The average value of a function f over the interval a to b is 1 over b minus a times the integral from a to b of f. So the good news is that this idea of average, it fits with what you already know about average. So I want to look at this problem. There we go. I have a metal wire. It's 8 centimeters long. So draw a little picture. And there is one end of it is getting heated. There's a little orange flame underneath it here. Orange flame. So this part of the wire is getting heated, and some of the heat is traveling down the wire. But if you think about it, the wire is going to be hottest near the end where it's getting heated. So that's why we have here, the further you go away from the heat source, you see how the temperatures are decreasing. Okay, so I have a metal wire, 8 centimeters long, and I know the temperature. I can measure the temperature at different places along the wire. I don't know the temperature at every place along the wire because I don't have a function. I don't have a function rule for the temperature. I just have these measured values. So I want to write an expression for the average temperature of the wire, and then estimate that average temperature using a trapezoidal sum. I'm going to move my little picture out of the way. I could do this. So I just learned right above this that the average value of a function, in this case t, is supposed to be the average temperature, so I need the average of the temperature function. It's going to be 1 over b minus a. Oh, so what are my a and b? They're the lowest and highest input values. So 1 over 8 minus 0, the integral from 0 to 8, t of x dx. This is an expression for the average temperature. If this were the AP test, that probably would have been worth 1 point just to write this expression. Now I'm going to have to find an approximation for that integral using a trapezoidal sum. So the part you want to make sure is that you don't forget your 1 over 8 minus 0. So this is going to be 1 over 8, and I'm going to add up the areas of a bunch of trapezoids. It says using a trapezoid for the 4 subintervals suggested by the data. So that means from 0 to 1, 1 to 5, 5 to 6, and 6 to 8. So I'm going to have a distance of 1 times the average of those two temperatures, so 100 plus 93 over 2, plus this distance between 1 and 5 is 4, times the average of 93 and 70. It's a 0, didn't really look like a 0. Average of 93 and 70, plus the distance between 5 and 6 is 1, and the average of 70 and 62, plus the difference between 6 and 8 is 2, and then the average of those two heights. So I'm going to get a calculator and simplify that. You should do the same thing. Okay, so I've been simplifying my expression. This is going to be 1/8 times 605.5 equals 75.6875. So we have to talk about the units. If I said, hey, what do you think the average temperature in California is? And what do you think the units would be? So it's going to be whatever the temperature units for the problem are. But we want to think about why that is. We want it to match up with this math that we did. So notice that we had, when we made these trapezoids, we were averaging the heights, which were measured in degrees. Was it Celsius or Fahrenheit? Okay, degrees Celsius. So we have degrees Celsius as their height, and a distance across the time, which was measured in, I should have checked it while I was there, centimeters. So degrees Celsius times centimeters, and then notice this 1/8. That 8 and that 0 are also measured in centimeters. So we're going to be dividing by centimeters. So we're going to have degrees Celsius times centimeters over centimeters. Now the fact that degrees Celsius times centimeters doesn't really make sense as a unit, you don't have to let that worry you, because notice the centimeters cancel out at the end, and we're going to have degrees Celsius as the unit. There's one other thing I want to point out. If you went off to the side and used your calculator and you tried to work it out, the most common wrong answer I would expect is 605.5. People sometimes forget to divide by the 8 at the end. So I just want you to promise me that every time you try to compute or estimate an average value of a function, in this case we were computing the average temperature. Look back at the